Hello and welcome back to Organic Chemistry 1. This week we are diving into Chapter 4, and Chapter 4 is all about alkanes. So alkanes, these are our first particular class of chemicals that we're going to study just as a group in a single chapter, and we're going to talk all about the reactions that they can do, how to name them, and a lot of different techniques that we're going to use for describing chemicals throughout the rest of the semester and into next semester as well. So, alkanes. Before we define what alkanes are, we want to define first this idea of a compound called a hydrocarbon. So hydrocarbons, you probably have heard this before. Hydrocarbons are just organic compounds that are composed exclusively of hydrogen and carbon. Now there's two different classes of hydrocarbons. There's what we call the saturated hydrocarbons, and then we have unsaturated hydrocarbons. Some of this nomenclature may seem familiar because hydrocarbons, you probably talk about this in terms of fossil fuels. You may know of fossil fuels as hydrocarbons, and sure enough, those are mostly composed of hydrogen and carbon. But then we also have this saturated versus unsaturated. So you may have heard that when you talk about fatty acids, for example, or saturated fats, like in things such as butter, and unsaturated fats like in olive oil, for example. So the basic difference between a saturated hydrocarbon and an unsaturated hydrocarbon is that saturated hydrocarbons have the full complement of hydrogens. So they have the maximum number of carbon-hydrogen bonds that can be present in a compound. So here we have two carbons. So those two carbons are bonded to each other, so one bond each. And that leaves them with three bonds open because we know carbon is tetravalent. Each of those three bonds on both of those two carbons is filled with hydrogens. So that's what we mean when we say saturated. You can think of it like it's a carbon-carbon compound that's saturated with hydrogens. And that's what that nomenclature means. The other way to think about it, and this is the way that I usually think about it, is that saturated hydrocarbons just are composed entirely of sigma bonds. There's no pi bonds involved in a saturated hydrocarbon. So that is what makes us, gives us the distinction from the saturated hydrocarbons to the unsaturated hydrocarbons. So as I mentioned, saturated has its full complement of hydrogens. Unsaturated, they actually have some pi bonds, so they lack some of the possible hydrogens. Like for example, we know that carbon-carbon has a single sigma bond here, but when we add an extra pi bond, that actually takes away two available bonds for hydrogens to be there. So rather than C2H6 that we have with ethane, with ethene, we have C2H4. So it's unsaturated. It doesn't have its full complement of hydrogens. Same thing with ethyne here, or acetylene. These are the common names here. This is going to get annoying in a little bit, but we'll talk about the nomenclature. So here we have two pi bonds, and that again is removing possible bonding sites for hydrogens, so unsaturated. And again, the easy way that you can tell unsaturated versus saturated is just look for pi bonds. If there's any pi bonds, then those are unsaturated compounds. This is also the reason for the distinction between unsaturated fats and saturated fats. Saturated fats are just long chains of carbon-carbon bonds that are fully, all sigma bonds. They have their full complement of hydrogens, whereas unsaturated fats have pi bonds involved, generally speaking, double bonds in one way or another. We'll talk about that later in next semester when we talk about lipids, but you may hear a little bit about that in your biology class as well. So yeah, so the distinction here is we want to point out, we're going to focus on this side here, alkanes. Those are our saturated hydrocarbons. So that's where we're going to start. And then eventually we'll get into alkenes and alkynes before the end of the semester. Okay, so where do alkanes come from? Again, I mentioned that you probably have heard this word hydrocarbons before because you can think of like fossil fuels as hydrocarbons, and sure enough, that's our most common source of hydrocarbons. So for alkanes, we basically can harvest these things from the ground as components of petroleum and natural gas. So you can get carbon chains of 1 carbon to 4 carbons long. This is from methane to butane. We'll talk about that nomenclature here very shortly. That all comes from natural gas. Methane is a large component of natural gas. Methane is also a really bad greenhouse gas. It's actually a worse greenhouse gas than CO2 per mole, if you want to think about it that way, because it absorbs a lot of infrared radiation. Now, after that, once we get into like pentane, for example, pentane is actually a liquid at room temperature, and that can be something that can be distilled from oil or other petroleum products. So C5 through C7, pentane through heptane, these are all very important solvents. And if we were in lab this semester, we'd be using each of them in various reactions. After that, and including down to pentane actually, all the way up to C12, so 12 carbons in a chain, these are all liquid components that can be used for gasoline. So gasoline, that's what we used to put into our cars when we had to drive places. That's the liquid component that distills off from 20 to 200 degrees from petroleum. So basically what you do is you dig an oil well, you get this liquid and gas that comes out. The gas that comes out is your natural gas. And then the liquid portions that come out, you send it into like a very complicated set of distilleries. And those distilleries can kind of isolate different fractions based on the boiling point. And again, this is something that you would do in lab as well this semester if we were meeting in lab. But we'll be teaching the techniques anyway. So the fraction that boils off from 20 to 200 degrees, that can be isolated and used in gasoline. Now above that, you actually get higher burning and higher boiling point hydrocarbons. This is what's used for kerosene and jet fuel. So jet fuel, of course, has a lot of energy in it. That's how jets are able to, burn that fuel and turn that into enough energy so that they can actually fly. Kerosene, of course, is important. It's something that burns but doesn't explode. Just keep this in mind if you ever have to start a fire in the future. Don't use gasoline to start a fire. Always use kerosene to start a fire. The reason is gasoline will evaporate. And so as you try to start the fire with gasoline, the gaseous components of gasoline will explode. And so this is what you see, like if you see a YouTube video of someone trying to start a fire and it catches them on fire, 90 times out of 100, that's because they're using gasoline to start that fire. So again, spend a little extra money, purchase some kerosene to start your fire. This doesn't evaporate appreciably at room temperature. So, so you can start your fire much more safely with kerosene. Then above that, you have like heating oil and diesel. So diesel is like a lower grade of fuel. It's not as useful for your car, for example. And then above that, you get like non-volatile liquids and then non-volatile solvents, things that are used like wax, asphalt, tar. And then the liquid components of that would be like a lubricating oil or a grease. So keep in mind, like this is just what comes out of the ground, kind of showing you here. And the gasoline fraction of this, the 20 to 200 fraction, is only about 19% of that. But of course, gasoline is going to be the biggest demand out of anything here. So you have to kind of find a new way to make it. So let's just talk about that real quick, which is what we call cracking. So what you can do is you take these larger alkanes. So like this alkane is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 carbons long. And what you do is you just heat it at high pressure, and it's usually over some kind of catalyst. So it could be like a zinc or a platinum catalyst. And with 200 atmospheres of hydrogen, that's a tremendous amount of hydrogen pressure. And at a very high temperature, 450 degrees Celsius, you can crack it. And basically what that means is you're breaking one of the carbon-carbon sigma bonds, but you're making, two smaller hydrocarbons, which can be then used for gasoline. So after you reform these straight chain alkanes and you crack the larger alkanes, you can actually get about almost 50% gasoline from your petroleum. Okay, so that's just like where we get alkanes from. And yeah, they come from the earth. As we're about to find out, they're extremely important. And so we're going to talk about nomenclature here in a second. So like what system do we use to name it? But just to re-emphasize, like there's a lot of organic compounds that you've heard of that you know the names for, but these are all like common names. So for example, there's formic acid here. So formic acid is named after the fact that it was originally isolated as an ant venom. And so it was named after the Latin word for ant, which was formica. So formic acid, that's this component, it's the acid component of ant venom. Urea, that came from urine, so urea, urine. Morphine, morphine's a painkiller, it's an opiate. It's derived from natural opiates. And so it's been used as a painkiller for quite a long time. As such, it's named after Morpheus, who was the Greek god of dreams. And then barbituric acid. So if you've read your Hunter S. Thompson, for example, or if you've read any of the poets of the 1960s, for example, they talk about barbiturates a lot. Those are like an old version of sedatives and painkillers and recreational drugs. This was discovered by one of the foundational organic chemists, Adolf von Baeyer. He was a German organic chemist. He synthesized many, many different compounds, including, most importantly, indigo dye, which was extremely useful for industry and among many other things. He also discovered this class of barbiturates, and he named it after a woman that he met, Barbara. So so sometimes, now imagine that, like, if we had to tell you this story for every compound that you're going to learn about in organic chemistry, it would get exhausting. Like there's no way we could do that. So let's bring it to a systemic portion here, a systematic naming system, which is what's called the IUPAC system. Now, you learned the IUPAC system for naming ionic compounds and diatomic compounds in your general chemistry class. So IUPAC, that's the International Union of Pure and Applied Chemists. That is our worldwide governing body. They're kind of in charge of a lot of different things, including the periodic table, and they also come up with the naming schemes for both inorganic compounds and organic compounds. So so this is what we're going to use to kind of name these different compounds throughout the semester. And basically what we're going to do from now on, like each chapter, once we get, I think, into chapter 7, the alkyl halides chapter, each chapter has its own kind of nomenclature portion, and then we talk about the reactions of those compounds after that. So just kind of keep that in mind here. So there's 3 things that we're going to figure out for the IUPAC system for organic compounds, starting with alkanes. Number 1 is we figure out the name of the parent chain. So what we're going to do is we're going to look at a structure, we're going to identify what's our longest carbon chain, and that's going to give us the parent name. After that, we're going to look for any branches. So any carbons that are sticking off of the parent chain, we're going to name those as substituents. Lastly, we need to locate those substituents on the parent chain so that we know that when we draw the structure back from the name, we're putting those substituents in the correct place. So again, that's just a vague overview. Let's look at some specifics here, and we'll do a bunch of examples as well. This is another thing where the more practice you get, the better off you're going to be on the test. Okay, so first up, identify the parent chain. And the parent chain is just the longest consecutive chain of carbons. So like when you look at this compound here on the left, you can think, if you just look at it, you might think, okay, I'm supposed to number this from left to right, 1, 2, 3, 4, 5, 6. And that's the longest chain that's left to right. But that's not the case. All of these sigma bonds can rotate and twist around. So you can make the longest chain whichever one you want. This is just one configuration of this molecule. So what you actually have to do is, it's almost like going through a maze. And the goal of this maze is to pick the longest path possible from one end to another. So as you can see, that would be 6. Now here I could go 1, 2, 3, 4, 5. Okay, now I have another choice here. So I could go 6 here, and another choice, 7, 8, for example. That's longer than what I chose before, but it's still not the best one. The best one is going to be what we have on the right here. 1, 2, 3, 4, 5, 6, 7, 8, 9. So again, just look for the longest consecutive chain of carbons. Don't worry about how it's written down on the test. I'm going to be trying to trick you, in the lecture assessments and all of that, into kind of hiding that longest consecutive chain. So my advice is just don't be tricked by me. Now, It is possible that as you go through it, there's more than one possible chain that's the longest. If you choose between two separate possibilities, you want to choose the one that has the most substituents that are attached to it. So let's look at these two examples here. So we've got two different pathways that goes to 1, 2, 3, 4, 5, 6, 7 carbons, or 1, 2, 3, 4, 5, 6, 7. So those are our two possibilities. Now, the correct one is going to be the one that has the most carbons that are branched off of it. So here we have 1, 2, 3 separate substituents, whereas on the right we have 1, 2 separate substituents. Again, those are groups of carbons that are off of the parent chain. So we want the one that has more. And the reason is that's going to actually simplify our nomenclature later on. It's going to make it easier to name. And so if it's easier to name, then that's going to be the correct one that we want to choose. Okay, now naming the parent chain. Basically, there's no way to do it except you got to memorize these names here. Now, some good news here. So we're naming alkanes. Each of these alkanes is going to end with ANE. And once you get to 5, you'll actually recognize some of these. These are the Greek prefixes. So pent is 5 carbons. So if you have a chain that's 5 carbons long, that's your longest chain. That chain, that parent, is pentane. Hex, hexane, that's for 6. 7 is hept or heptane. 8, oct, octane. 9, non, nonane. And 10, dec, decane. Now it's 1 through 4 that's a little bit different. Again, 1 through 4 you're going to have to memorize. So there's no way around it. It's just you got to memorize them. So 1, meth, methane. 2, ethane. 3, propane. 4, butane. And then once you get to 10, I guess we'll go up to 15 and tell you to memorize these here. It's very rare that you'll go beyond, for example, 15. But if you do have these possible combinations where it's icosane would be 20, triacontane would be 30, tetracontane would be 40, pentacontane 50, and 100 would be hectane. So yeah, but again, just focus on the first 15 here and that'll do you good. Okay, now one more thing. It is possible that you could have a ring of carbon atoms where the first is bonded to the last. So for example, here we have a 3-carbon chain, 1, 2, 3, where the 3rd carbon is bonded to the 1st carbon. That's a ring, right? So if it is cyclic in this way, what you're going to do is you're going to add the prefix cyclo in front of the parent name. So here we have 1, 2, 3 propane, and it's cyclic, so it becomes cyclopropane. Same here, 1, 2, 3, 4, that's butane. It's cyclic, so it's cyclobutane. Finally, 1, 2, 3, 4, 5, that's pentane. It's cyclic, so it's cyclopentane. So don't forget that. All right, so now let's go ahead and practice here. Let's identify and name the parent chains for each of these. I'm going to pause the video here. I recommend you pause the video, identify the parent chains, then we'll identify them together when I start the video back up again. All right, and we're back. So let's go ahead left to right. Let's try to identify the parent chain for each of these and name it, since we just learned how to do that. So starting on the left here. So let's just go left to right, and then we'll worry about a decision when it comes to like whether we go left or right. Think about it that way. So this is carbon 1 goes to carbon 2, carbon 3, carbon 4. So if we go down, there's only 1 more, and then if we go up, there's 2 more. So that means this is carbon 4, carbon 5, carbon 6. So that's 6 total carbons. That should be hexane. Next up. So going left to right again, just for no particular reason. 1, 2, 3, 4. Okay, so we have to decide. Now this could be 5, 6, 7, or it could be 5, 6, 7. Now if we were to go 5, 6, 7 here, that would give us 1, 2 substituents. Whereas if we go 5, 6, 7 here, that gives us 1, 2, 3 substituents. So remember, the correct parent chain is going to have more substituents. So we want to just keep going left to right, 5, 6, 7. So we have 7 carbons, that is heptane. Finally, so we've got this big ring here. This big ring is definitely going to be our parent chain, considering over here we just have a methyl and a methyl group over here. Let's go ahead and just number our way around the ring. So I'll call this carbon 1, 2, 3, 4, 5, 6, 7. And then that goes back to the first one here. So 7 carbons in a ring, 7 carbons would be heptane, and then it's in a ring, so that means it's cycloheptane. So cycloheptane there. Let's go ahead and clear that up. Again, you'll want to practice with this a bunch, but this is the first step in a longer process. So let's keep it going before I run out of time here. Okay, next up, we've talked about these substituents, right? You want to pick the chain if it's tied that has the most substituents. So now let's go ahead and talk about how we name them. So again, the parent chain, that's the longest one. So this in this case here that we're looking at, it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's decane. And then the substituents, those are any branches that come off of that parent chain. So here, for example, this substituent has 1, 2 carbons on it. Remember, this carbon is on the parent chain, so that does not count as part of the substituent. It's just that it branches off and it's got 1, 2 carbons there. So here's how we're going to name the substituents. If we had 1, 2 carbons in a chain, it would be ethane. To name the substituent then, we drop the A and E and we add YL. So ethane becomes ethyl, ethyl. Down here, this is 1, 2, 3 carbons on a substituent. 3 carbons would be propane. Propane as a substituent becomes propyl. And lastly, we just have a single lonely carbon over here. You've heard me say this before. This would be methane. It becomes methyl. We talked about methyl groups in several different chapters already. So this is kind of like just formalizing what that name actually means. So yeah, so we're going to name those substituents YL instead of ANE. Okay. Now keep in mind that the ring that you see in a compound can be a parent chain or it can be a substituent, just depending on the number of carbons. So here we have a cyclohexane here. This cyclohexane is the parent chain because it's got a 3 carbon chain attached to it. So the more carbons that you have, that becomes the more important or the parent chain. So cyclohexane is the parent here. The propyl is the substituent. So this would be propyl cyclohexane. Now over here, we have a cyclopropane, and then we have a 1, 2, 3, 4 butane. Well, 4 carbons is greater than 3 carbons, so that means butane is going to be our parent chain, and then this cyclopropane becomes cyclopropyl as a substituent. So this becomes 1, we'll talk about what that means, cyclopropyl butane. And again, there's more practice in your book. I just always have these little notes down here. This would be Skill Builder 4.2 if you're following along in your book. We have a bunch of practice though coming up, so don't worry too much about that. Now that's for simple substituents. Now sometimes you're going to have complex branches as well, so that's something that we want to keep in mind too. So here, for example, like when we name this, we have the parent chain first. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That's undecane, okay? So that undecane, there's no way that we're going to include this as part of the parent chain because we have to go with the longest carbon chain for the parent chain. So now all of a sudden, we not only have a 1, 2, 3, 4, it's like a butyl group, but then this butyl group also has a methyl group on it. So sure enough, that's how we have to number it, in fact. We basically do a sub-nomenclature problem looking at this complex substituent. So now let's look at this complex substituent. Let's ask ourselves, how would we name it if it were its own compound? Well, we count 1, 2, 3, 4 carbons total. That's butane. So we know it's going to be a butyl group. Then we're going to number it. And this is something that we do for the next step anyway when we're naming these full compounds. So this isn't going to be too hard. But we have the methyl group here is on the second carbon. So we're going to call this 2-methyl-butyl. 2-methyl-butyl. So the numbering scheme, again, is just that the first carbon is the carbon that's going to be attached to the parent chain. So this is always carbon 1. Then, of course, whatever the longest subchain here is, you just number that. So 1, 2, 3, 4, that's a butyl group. There's a methyl on the second carbon, so it's 2-methyl-butyl. So it's, again, it's like a sub-nomenclature problem within the nomenclature problem. Now, there are some branch substituents that do have common names, and you'll actually have heard of a couple of these before already. So for example, you could have a propyl group. That's where you have 1, 2, 3 carbons. But what if this propyl group was actually bonded at the second carbon here? Well, we have a special name for that because it's a really common substituent. It's also called isopropyl. So you probably have heard of isopropyl alcohol. It's exactly what you think. It's an isopropyl group where this parent is then, it's just an OH group. It's an alcohol group. So that's rubbing alcohol. Now, it's a little more complicated when we go up to 4 carbons, the butyl groups. We have 3 different branch chain ones that have their common names. And you'll just have to memorize these as you go from it. So here you have a butyl group, that's a straight chain here. Now, if it's bonded at this second carbon instead, that's what we call sec-butyl. So, and you have to write out SEC, sec-butyl. Now, if instead you have this kind of substituent here, where it looks like it's an isopropyl group that's bonded to a methyl group that's bonded to the parent chain, that's what we call isobutyl, again, because it resembles structurally the isopropyl group. And then finally, if you have, oh, I'm sorry, let me go back. If you have a central carbon that's bonded to 3 methyl groups here, sure enough, it's 1, 2, 3, 4 total carbons in the substituent, but this carbon here is a tertiary carbon. In other words, it's bonded to 4 other carbons. So we call this a tert-butyl group. So again, these are names that you're just going to have to commit to memorizing. But it won't be that hard. There's only really 4 of them you have to memorize. Just those 4. And the rest of them, you can just learn the systematic naming for them. Okay, so now we've got the parent chain. We've got the names of the substituents. Now what we have to do is we have to number the parent chain. And it's not as simple as numbering left to right. For example here, so here we have 2 different examples of methylpentane. We have a methylpentane where the methyl substituent is on the second carbon. So we number it left to right, 1, 2, 3, 4, 5. And then the methyl group is on the second one. So that becomes 2-methylpentane. And we just put that all together. Now here, you could also have the methyl group on the middle carbon. So you could number it 1, 2, 3, 4, 5, or right to left, 1, 2, 3, 4, 5. Symmetrical, so it doesn't actually matter. This becomes 3-methylpentane. Note the style guide here, basically. You're going to put the number, then a dash, the name of the substituent, and then smash it right on top of the name of the parent chain. So 2-methylpentane is kind of how you can look at it there. So now, how are we going to number it? Well, there's kind of simple ways to number it, and then things that get a little bit more complicated. So let's start with the simplest example first. And this simple example hopefully will make sense. If you only have 1 substituent, you want to number it so that you're going to number the parent chain so that the substituent is on the lowest number of carbon possible. So here we have 2 heptane. We have a heptane, right, that has a methyl group on it. So we can number the heptane left to right or right to left. Well, left to right gives us 2-methylheptane. Right to left gives us 6-methylheptane. Our goal is to keep that number as small as possible. So sure enough, numbering it left to right is the correct way to do that. Now, when you have multiple substituents, you actually have to number it so that you're going to give the first substituent the lowest number possible out of all of them. So don't try to like average the number or anything like that. It's not that complicated. If you have multiple substituents, you just want to make sure that that first number is the lowest possible. So looking here, now we have heptane again, but it's tri-substituted. So we have methyl on carbon 2 and 2 methyls on carbon 5. If we number it left to right. If we number it right to left, that gives us 2 methyls on carbon 3 and 1 methyl on carbon 6. So the question is it 2,5,5 trimethylheptane, or is it 3,3,6 trimethylheptane? Well, the answer is, again, you want the lowest first number possible. So what we're going to do is we're going to number it so that we have the 2 rather than worrying about like 3, 3, and 6. So the 2 beats the 3 is the way that you can think about it. Now, if there's a tie between the first one, then you move to the second one. So like, for example, here we have a methyl group on carbon, on the second carbon, whether we number it right to left or left to right. So both of these are 2-methyl. So that's not going to change anything. Then you go to the next one. And the second methyl group, well, if we number it left to right, that gives us a 5 on that methyl. Whereas if we number it right to left, that gives us a 3. So then the second substituent becomes the tiebreaker. Now, if there is no other tiebreaker, whereas like none of that applies, what you're going to want to do is you assign the lowest number to basically what you're going to do is you assign the lowest number alphabetically. So go on the substituent name and ask yourself which one comes first in the alphabet. And I know that seems a little foolish, but you're going to have to pick something. So this is the way that we picked how to do that. So like, for example, here we have a bromine and a chlorine as a substituent. We're going to learn this soon, but a bromine as a substituent becomes bromo. A chlorine as a substituent becomes chloro. So this could either be 1-bromo 5-chloro pentane, or it could be 1-chloro 5-bromo. But as we're about to find out, this would become 5-bromo 1-chloro pentane. So what we want to do is we actually want to just give that number to the first one alphabetically. And so 1-bromo becomes more important, and that beats the 1-chloro. This is also true for cycloalkanes, although for cycloalkanes, you have to consider basically like you can start at any of these here. You don't have to start at one end or the other. You're just going to start on the carbon that has the most substituents, going to the second carbon that has the most substituents, to the third carbon, etc. So here it makes sense that we're going to have 1,1,3 trimethyl versus 1,3,3 trimethyl, because the second methyl group should be on the first carbon rather than on the third carbon. Okay, so now we've got our parent chain, we've got our substituents, and we've got our parent chain numbered. So now we're finally ready to actually put all the name together in one little name. So this is our nomenclature problem here. So here's what you do. You put the number and name of each substituent before the parent chain name in alphabetical order. If you have multiple substituents that are identical, so if you have multiple methyl groups, for example, like let's say we have 3 methyl groups on the same one, it becomes trimethyl. You bring that methyl groups all together and that becomes trimethyl. If you have 2, it's di, 4 is tetra, 5 is penta, and then from there it would be like hexa, for example. Now, a little annoying. When you're alphabetizing the substituents, you're going to put them together in alphabetical order. But dimethyl is going to be alphabetized the same way as methyl is going to be alphabetized the same way as trimethyl. You ignore di and tri when you're alphabetizing those substituents. Okay, so there we go. It's our 4-step process. So always refer back to this 4-step process. Number 1, find the parent chain. Name the parent chain is what I would say next. Next step, identify and name any substituents that you have. Then number the parent chain, and you're going to assign a number to each substituent. That number is going to be what carbon is it on the parent chain. Finally, the last one is list the numbered substituents before the parent name in alphabetical order. Ooh, so that sounds like a lot, but this is a thing that with practice, it's going to become second nature to you. This is going to be a way that we can easily name different organic chemicals and communicate with one another in this class in the future. So I know this was a long lecture, but let's go ahead and give it some practice. So let's go ahead. I'll do the first one here with you together. And then what I'm going to do is I'm going to pause the video with sample exercise number 2. We'll go over the names together as well once we're ready for that. So Let's go ahead and back up here. So first up, we've got this compound. Number one, we want to identify and name the parent chain. So when we look around here, we have an ethane possible. We have a 1, 2, 3, a propane, and then it's a methane and a methane. Or, of course, we have the cyclic structure in the middle. That's a cyclohexane. 1, 2, 3, 4, 5, 6 carbons in a ring. It's cyclohexane. So that's the parent name. Then let's go ahead and identify our substituents. So here, I'm going to use the annotation real quick. So here, this is a 1, 2, 3, 4 carbon substituent. You may remember, you may recognize this. This is one of our butyl substituents that has a special name. This one's called tert-butyl. This here, this is an ethyl group. And then these guys down here, these are each methyl groups down here. So I'm just going to type this out so that we're kind of following along. This up here, we recognize it's butyl. Then all of a sudden we look and we see, oh, it's the tertiary butyl group, so tert-butyl. This here, this is a substituent that's 1, 2 carbons long. That's an ethyl group. And then down here, we have each just 2 little methyl groups sticking off of this carbon down here. Now next, we need to figure out where we're going to start our numbering scheme from. So we could start it from this carbon, or this carbon. We know that basically we want to minimize the numbering one way or another. So the way that we're going to do that is, if we look down here, well, I kind of wonder now. I'm looking at this here. I think the way that they have this numbered could be wrong actually, because I believe the way that they numbered this is they numbered it from tert-butyl, and then 2 going to ethyl, and then 4 for dimethyl. But if you try to actually minimize the numbering scheme, the first one could be tert-butyl, and then the second one would be ethyl here. That'd be 1 tert-butyl, 2 ethyl. But if you think about it, if you numbered this one as 1 down here, this would be 1, 1 dimethyl. So the second substituent would be on the first carbon. So I think that would actually be the better way to number this here. I stole this slide from your book, so please blame your book on this and don't blame me. So let's go ahead and let's number it that way real quick. Here we're going to just press escape. Stop our annotation, clear all the drawings. There we go. We're going to escape, get rid of this here. And we're going to number it, we're going to name it that way. Now this gives us 1, 1 dimethyl. So it's 1 methyl, 1 methyl. So then do we go to the left? Do we go to the left to number it, or do we go to the right to number it? Or we're going to try to get closer to the substituents here, right? So this becomes now 3 ethyl. And then on the opposite side, that's 1, 2, 3, 4 tert-butyl. So now when we put that all together, when we name it, we're going to start with alphabetical order. So remember, tert-butyl, that's going to be named based on the butyl substituent here. So that becomes 4 tert-butyl. And then, so B comes before E comes before M. So that's 4 tert-butyl, 3 ethyl. And then we have 2 methyl groups. So these 2 methyl groups are both on carbon 1. So that becomes 1, 1 dash dimethyl. And then we give it the parent name, cyclohexane. Okay, so I believe that's a better name than the one that we had before. So I'm going to leave that there in our slide. And let's go ahead and let's do the sample exercise here together. Now, that was a little sloppy, so let me do one more with you. Let's go ahead and let's just do the top one here together, and then let's try to, I'll let you guys work on the second, and we'll go over the answers here together. So first step 1, identify the parent chain. So remember, it doesn't have to start from this carbon here. In fact, oftentimes I'm going to write this carbon out here, and it's not going to be part of the parent chain. And so this kind of makes sense. If we actually look at it, we're going to start from this carbon down here, because this is going to be 1, 2, 3. It's going to give us carbon 3 here, whereas if we started here, that'd be 1, 2. So let's go ahead, start with that. 1, 2. 3, 4, 5. Okay, now it could be 6, 7, 6, 7, or 6, 7, 8. Okay, so 6, 7, 8, that's got to be the longest one. So 6, 7, 8. All right, now real quick, what's an 8-carbon chain? Octane. Okay, so that's our parent chain name. We're going to come back to that, but I always just like to write that down first because now, okay, we know that. Next up, let's go ahead and I'm going to switch my colors here. Let's go ahead and identify our substituents. So here we've got this is a substituent, this is a substituent, and this is a substituent. And let's go ahead and name it. So over here, this is just one carbon that's sticking off. That's a methyl group. Down here, we've got 1, 2 carbons sticking off. That's a methyl group. Oh, I'm sorry, ethyl group. I don't know why I typed methyl. And then over here, I was looking up here probably. This is just one carbon sticking off again. That is a methyl group. Okay, so we have one ethyl group and we have 2 methyl groups. Now let's go ahead and take a look at the numbering scheme. So if we start down here, this gives us 1, 2, 3 as our first substituent. Starting up here, 1, 2, 3 as our first substituent. And to be clear, we have to start on either end. It has to start at either this carbon or this carbon here. It's not like the cyclic one where you can choose any point along the ring. You have to start at the end point, right? So, okay, so it's tied on the first one. That means we go to the second one. So here it's 1, 2, 3 as the first, and then 4 is the second. Starting from this side, 1, 2, 3 as the first, 4, 5 as the second. Okay, so that tells us that we actually need to start numbering from up here. That's got to be carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, carbon 6, carbon 7, and lastly, carbon 8. Okay, so now we're ready. Oh, can I edit this guy? Okay, so we're just going to add these in front then. So that means that we've got an ethyl group and 2 methyl groups. The ethyl group is on carbon 4, and the methyl groups are on carbon 3 and 6. So we know that it's going to be E comes before M, so that becomes now 4 ethyl. And then we put a dash, and now we've got methyl groups on carbons 3 and 6, because that's 3, 6 dash, and then there's 2 methyl groups, so it's dimethyl. And when we put it all together, here, let me use my selector here real quick, because remember, you're going to smash these together. So here's the final name of the compound, 4-ethyl 3, 6 dimethyl octane, and it's all smashed together just like that. Okay, so I know it's a lot, but let's go ahead and work on it here. Why don't you guys go ahead, work on the next 2, and then I'll go over the correct names with you once we pick up in the video. So I'm going to pause the recording here. I'm going to come up with the correct answers here. I recommend you pause the video as well, work out these last 2 problems in your notes, and then we'll go over the correct answers together. All right, we're back here with the answers. So just want to go through the answers here, and you can make sure to comment any questions that you have on Canvas. That's kind of the easiest way for me to see your questions there. And we've also got some practice with the lecture exercises coming after this. So make sure you take a look at that PDF and get some more practice there. But first, let's go ahead and go through these here. So identify the parent chain here. It's 7 carbons long, so it should be heptane. Then we've got 2 ethyl groups. So here and here, so it's going to be diethyl, and then we've got 1 methyl group here. We're going to number it this way because starting from this side, that gives us a 2 methyl and a 3 ethyl. So the 2 methyl basically wins out. That's the first substituent from either direction. So that gives us now 3, 5 diethyl, 2 methyl heptane. And then down here, cyclopentane, that's got to be, we just have a ring here of 5 carbons, so cyclopentane, that's our parent chain. Now we could start from this methyl group because we're going to number it 1, 2, 3, or we could number it from this ethyl group 1, 2, 3. So ethyl versus methyl, this falls down to alphabetical order, and ethyl comes before methyl, so that means this has to be carbon 1. So it becomes 1 ethyl dash 2, 3 dimethyl cyclopentane. That should be our answer. Okay, all right, well, that'll do it for our nomenclature section. So go ahead and give it a shot in the lecture exercises as well, and ask any questions that you have in the comments below, and I'll see you when we talk about some different consequences of this alkane, of these alkanes.